Hello everyone, today we will be going over stacks today, and without any further hesitation, let's get started. So stacks in general can be thought of as a stack of plates, and typically already abide by the principle of last in, first out. So imagine if you're stacking a series of plates in particular, the first plate that is at the bottom, that's the first one, and then it continues accordingly. And then with stacks in general, there are functions as well, 3 of them in particular, called push, pop, and peek, where they all encompass in particular how the data structure actually behaves in general. And stacks are very efficient in terms of space and time complexity. For stacks have a space complexity of O of n and a time complexity of O of 1, making them very efficient. And now let's go over our practice problem. So we're given the task to implement a stack using an array, and then after we have already completed our array, we will then use a linked list to be able to create a stack. For stacks can be made from either an array or linked list. And we will perform the following operations. 1, we're going to push an element onto the stack. 2nd, we're going to pop an element from the stack. 3rd, we're going to peek at the top element of the stack. And finally, we're going to check if the stack is empty for when we are constructing a stack using an array as well as a linked list. So first things first, we are going to make our stack using an array. And so the way we are going to be doing this, first and foremost, and as usual, must include our libraries, which should be include iOS stream, depending on what code editor you're also working with, and then using namespace std. And I'm going to be creating a class called stack that will be called publicly. And we're going to have an integer called top, and a constant static int called max size. I'm going to make this 3 since we're going to put in 3 different elements inside the stack, an integer of array, and we're going to use max sizes because arrays are used in a fixed sized setting. Let's put this right here. Then I'm going to create a public instance for stack. We're going to initialize, and then we'll do top minus 1 because arrays always start with 0. Are indexed at 0. That's the best way of putting it. Let's see if I can just move this over a bit. Okay, we're good. Now we're going to focus on pushing, popping, and peeking at the stack, and then check if empty. So what we will be doing in order to push is I'm going to have a Boolean condition called push, and I'm going to have an integer, let's call this x, that we will be creating through our Boolean. And then we're going to have condition statements. So since we have an element called top already, if top is greater than or equal to the max size of the following array, minus 1, then we will indicate a stack overflow. And finally we will return false. And else, in this case, that means that we can add on to the stack, and this part is really crucial. So sometimes whenever there are additional operators or decrement operators as well, people would typically operate like this, but in this case, since we're dealing with a stack, we are going to be doing it this way because pushing elements into a stack, again, it's like a stack of plates. You start from the bottom and you work your way up. And I'm going to redeclare that as x, and then return true. So that's a Boolean condition, and then we'll make the following actions of when to add an element. I'm going to fix this actually. There we go. And the next part we're going to be doing is popping. So we will be actually using an integer, not a Boolean in this case. So just showing a different technique because we are popping a specific element from the stack. And so what we'll be doing is that we are going to be checking if the top is less than 0. That means that there will be a stack overflow as well, since there are technically no elements to be able to pop. But in this case, it's called a stack underflow. No elements to pop. And we return 0, since in a similar construct with what we have for the Boolean condition as well as the int, in this case we will return 0, but Boolean conditions return true and false in that case. Then otherwise what we will be doing is that we are going to redeclare x to be this part, where we'll have array and we'll decrement there, because whenever we are decrementing, again, as mentioned before, stacks are like a series of plates. Whenever you are deleting something from the stack, you take it directly from the top, and we decrement accordingly like this, versus pushing, where we're doing it in this format as well. And then we're going to return x. There we go, and then we will be peeking. What we'll be doing the same thing that we did with the pop, as well as taking elements from the Boolean condition as well, where we will be returning 0 and then returning the exact element as well. So what we will be doing is this int peek, since we're going for a specific element that we have. If the top is less than 0, we're going to output stack is empty. And we always settle with our edge cases as well, and L, return 0, and then else. We're going to return the specific element at the top. For we're not altering or anything else, we're just getting the info really. And then finally we're going to check to see if it's empty, so that means we will be doing a Boolean condition is empty. We're going to initialize that function, and then we will be returning the top if it's less than 0. That means it's true. It's empty. For whenever we have an array, arrays always start with 0. But if it's less than, then therefore we know it's empty. Now, to be able to test this bad boy, what I'm going to be doing is that we're going to have our main function that we have over here, and then I'm going to declare our class that we have, a stack, and then we'll have stack over here. I'm going to stack push, let's say 10, for instance, that's the specific element right here, then 20, then 30, and then what I'll be doing is I will be outputting, let's pop from the stack first. I'm going to be, I'll just indicate. So we are push into stack. We already pushed the elements, pop from the stack, and then we will be peeking from the stack and check if element is empty, just to combine two birds with one stone really. So stack.peek. Our element at the top. Sorry about that. So we're going to be popping from the stack. Stack.pop right over here. There we are. And it should pop actually 30. Then we're going to peek for the updated. Peek should be 20 since we popped directly from the stack, and then we're going to peek. Elements in the stack. Now, this is the part where we're going to be using our is empty. So while the stack is not empty, hence the exclamation mark over here, we're going to output count stack.peak. In total, and finally we're going to stack.pop to empty out all of the rest and return 0. Alright, and I'm also going to have this in the comments as well. Let's just run this. There we go. So we pop directly from the stack that we have up here. 20 is our element at the top, therefore, after we have checked our popped stack, and the elements in the stack in general are going to be 20 and 10 all together. This pop is not technically needed in particular, because then it's just going to have 10. So we can just run this entire program as well. Yep, updated stack. Stack is empty, as it's already indicated after we peaked, and it calls upon this. There we go, that makes sense. And yeah, this was the stacks for built off from an array. So let me just zoom out. There we go. This is a full look over here, and I'll have this in the comments as well. And now let's go over the second part for our practice problem, developing a stack using a linked list. So to be able to get things started, we always include our libraries that we always need just based on general principle. So include a stream, and then we will be using namespace std. I'll have a class called stack. And what we'll be doing, since linked lists are made of nodes in particular, and the benefit of linked lists are that they can be added dynamically, so we don't need a fixed amount compared to an array, and this provides greater flexibility as well, while keeping an efficient space and time complexity. So we'll have a struct stack node, which will be called entirely inside of our class. I'm going to have int data, and then we're going to have stack node next. This is how we construct nodes inside of our linked list. And we will initialize a top. So stack node is going to have a top node as well, since stacks are comprised of, or structured like a series of plates, last in, first out. Now, all right, I will be creating a public instance, and then we're going to initialize our function that we have for top null pointer. That's how we just initialize inside for linked lists. And then we're going to put our function push pop peak and is empty. And I'll just put this here to make sure it just stays quiet. So to push, I'm going to have a function called void push int x, and then we're going to initialize our first node. So stack node here, new node is equal to new stack node right here. And then if the new node is not there, hence the exclamation point, we will be outputting a heap overflow. No nodes detected. Always have an edge case. We always start with our edge case. Return there And then what we will be doing is that we're going to be linking up every piece of data with our new node. So new node data that we can use. We can even call this next as well, just to make things better. Or actually, data. Yeah, that's better. It's actually going to be calling upon just a raw data point over here, equal x, the new node to the next one, which will be referring to, because we're putting in our data inside, I'm referring that as x. And finally, we're going to put this one as the top, and then we will re-declare as new node for top. So that way we're still stacking on each other. And now we will be focusing on the pop. Now we can do the same thing we did before by using an integer function as well. And for peak, I'm just going to do the same thing that we did before. In peak, then is empty, bool is empty, to be able to fill out everything else. So pop, we have here if there's nothing at the top, then we have a stack underflow. Nothing at the top, we'll return -1. And this is what we will be doing. We'll be doing this technique called a swap. So we're going to have a stack node temp equal top, and then top is going to be equal to top to the next node that we have that we're referring to. That is just considered a placeholder in that case whenever we are putting in more data. And I'm going to have another integer called the actual popped element. Popped temp data. And then finally we're going to have this function that is already called within C++ called delete, and we'll delete this temporary node that we made to be able to use it as a placeholder, and then we're going to return our popped. So what it's doing is that it's actually getting the data from our temporary node that we have. And inside of our temporary node that we have made, that we are scanning throughout the rest of our entire linked list. Hold on, give me a second. There we go. No equal sign right here. Yeah, it's just complaining because there's nothing right there. Okay, there we go, that makes sense. So it's really getting the exact data point inside of the temporary node we have made. And since we are scanning throughout our linked list, because linked lists are comprised of a head and then a series of nodes as well, especially if we're using a singly linked list at the same time, which is the most conventional way that a lot of linked lists have been developed. So this is just one direction that we can do. You can develop a stack with a doubly linked list, but for the sake of convenience, we're just focusing on a singly linked list in this case. And then I'm going to be focusing on peak. So if there's nothing at the top, we can say that stack is empty. And then we return -1, not 0 in this case, because we're dealing with linked lists. So totally different. So linked lists use functions, and arrays like to use booleans and integer functions as well. Then we will return the top data as well, because the top data is looking at the specific element inside of our top component for our stack. Then we will this function for boolean will be pretty simple. We will have return top equal null pointer. It's indicating if it's true as well. And for the sake of everything, I'm just going to create another function to print out our stack of linked list nodes. So that means in particular, I'm just going to call it void print list as well, much like what we did in the linked list video as well. So print list, what we will be doing if is empty. In this case, as an edge case, we always think about edge cases first. Count stack is empty, and we end it, and we just simply return. And then we'll have a temporary node as well, indicated as the top. And because what we do for linked lists in general, we always print directly from the head and the rest of the nodes. This explains its efficient space complexity, while temp doesn't equal a null pointer, meaning that there is something there. We're going to output temp data, and then temp is equal to temp next. Finally, we will be outputting everything until the very end of our list, depending on the context of what we have. So I'm just going to call this printing out our list. Okay, there we go. So push, pop, peek, checking if it is empty, and having a function right here to print out and check for everything as well. Now, let's go over to our main function, and what we are going to be doing, we always initialize or call upon our function, call upon our class and declare. Then I'm going to push, and I'm going to pop, peek, then print out everything. So that means we're going to have stack right here. I'm going to call this stack. Then push. I'm going to have stack.push, element of 10. We'll do the same thing we did before. Now notice, in arrays, we always need a fixed size, but linked lists are very efficient because you don't need to have a fixed size, and you can add them dynamically. So right here, this is how we push. Then I'm going to pop something from the stack. So popped 30 from the stack. There we go. Then peek. Our top element, and then end that, and then we're going to print out everything. Our updated stack. Sorry, print list. There we go, that's better. Return 0. Just build everything and make sure it's good. All right, build succeeded. And let's run this bad boy. There we go. Yep. All right. So we have main, print list, which displays everything, checks to see if the stack is empty, checks the peak of the stack, pops it, and then pushes each new element accordingly into our stack. And looks like it did pretty well because it goes last in, first out. We push each element accordingly, 30, 20, 10, and we have already done our necessary functions. So let me just zoom out here, be able to help you folks see. And I'm also going to have this in the description as well, or actually the comment section. Yeah, there we go. So feel free to take a few screenshots of this as well. And yes, so this was stacks over here. Hey everyone, thank you again for taking time to watch this video. If you found this video helpful, be sure and feel free to please like and subscribe. And if you have any other questions as well, feel free to put it in the comment section. And as always, take care. Cheers. Bye-bye.